Hi guys, my name is Clara Hawkins, and today I'm going to be walking you through my experiment of a ball rolling across a table at a constant velocity and how those results compare to a simulated version. Through this experiment, I wanted to be able to compare the real-life experiment to a computational model of a rolling object's velocity. In doing so, I learned the impact of net forces and the input they have on momentum and velocity of an object. The models yielded from this experiment were graphs of the actual position time model of the tennis ball and the computational predicted position time graph found through GlowScript. These will later be compared to analyze the experiment. I will go into more detail about the physics principle on the next slide, but an important principle to keep in mind is Newton's second law that provides the relationship between the forces on a system and their impact on velocity, position, and momentum. In this experiment, we can expect to see a close correlation between the predicted and actual graphs, barring the influence of unaccounted for forces. As I mentioned in the previous slide, Newton's second law is integral to understand why this experiment works the way it does. The second law states that an object in motion at a constant speed will stay in motion at a constant speed unless an object has an outside force acting on it. This means that if F net is 0, an object will keep its tendency to move in the way that it is currently. The position update formula is an important formula to utilize throughout this experiment because it shows how we can predict the final position if we know the velocity is constant, or alternatively, we can find the average velocity if we know how far the object traveled and for how long it traveled. Additionally, we can use the velocity update formula to prove that there is no net force acting on a system if V final equals V initial. For this experiment, I define my system as the ball and the table that it is rolling across, and the surroundings include the gravitational pull and any air resistance / wind that may have been present. My initial conditions will become important when coding for the computational model, so some important things to note is that the ball is rolling along a table with little friction and no force is currently being used to push the ball to the left. The position that I started recording data from was 0.763 meters, and the velocity at this time was 8.48 meters per second. My experimental setup consisted of first finding a smooth surface with as little friction as possible, pushing the ball, and then recording the movement while it was at its most constant speed. I collected my data using the tracker program. I weighed the tennis ball I used, and I also measured the diameter so I could calculate the distance the ball traveled in tracker. I also lined up the axis to be in line with the table and set the origin of the ball's starting position. Then, using the track function in the program, I assigned a point in the center of the ball for each time frame. To begin the analysis, I first had to find the computational experiments graph through GlowScript. This was a code that I will describe in the following slides. Once this is done, I transferred both the GlowScript position time points and the tracker position time points into a spreadsheet. Then I inputted these data points into a scatter plot so the slopes or the velocity of these lines could be compared to check for accuracy. This slide depicts the data from Tracker and GlowScript that was used for the scatter plot. Feel free to pause for further analysis, but the results will be shown more clearly in the graph later. This slide is going to explain how I collected the data that I showed previously using the GlowScript coding software. Using the starter code provided, I replaced the weight with the weight of my tennis ball, 0.056 kgs, and I replaced the velocity and the position initial conditions with the ones I previously stated. I found my delta t by observing the time the tracker assigned in between frames, which is 0.033 seconds. I knew I wanted my F net to be 0 since the ball needed to move at a constant speed, and Newton's second law tells me that there is 0 net force acting on the system if the ball is moving at a constant velocity. This also tells me that the second part of the next equation will zero out and the ball's initial velocity will equal ball's final velocity. The last part of the code is the position update formula that was used so the program can calculate the final position given the total time tracked, the starting position, and the average velocity. These are the graphs that resulted from the GlowScript code. As expected, the slope of the position time graph is constant since there is no net force causing a change in velocity. This is also why the velocity time graph is a flat line since there is no acceleration. The result of this experiment are shown in the scatter plot comparing the predicted movement of the ball in blue and the actual movement of the ball in red. As you can see, there is some disparity, especially towards the end. The computational graph has a steady slope due to the velocity being simulated to be perfect. However, the slope, or the velocity, increases towards the end of the experimental graph, likely due to human error. Some other sources of error to consider are disparities in the amount of friction when the computational model is assuming no friction, or I did not manually create a perfect constant velocity, or that the table might have been a slight slant causing it to accelerate towards the end. Finally, we are going to discuss the questions for the end of the experiment. If the axes were to change, the slope of the line would switch from positive and direct to negative and indirect relationships, since the rightward direction would then be classified as the negative direction. This means the velocity would be negative, but the speed is constant since it's not a vector. It is very difficult for us to determine all of the possible forces that are in the system, but we can pinpoint some of the most influential ones. For instance, we know that the normal vector exerted upwards on the table is equivalent to the downward gravitational force of Earth, since the ball is not moving vertically. However, the horizontal forces are more complex since we don't know about the extent that friction is impacting the ball's horizontal movement.